Okay, Chapter 8. The title of Chapter 8 is Series Solutions of Differential Equations. Of course, what we're talking about here is power series and Taylor series, so you're going to have to review, if you need it, that material from Calc 2. If you haven't thought about that or looked at that in a long time, now would be a good time to be reviewing it. So let's look at some stuff that remind you of a few things. So first of all, the Taylor series for a function f of x is the following. It's the sum as j goes from 0 to infinity of the jth derivative of f, and remember the 0th derivative, that's just the function itself, evaluated at x0. This number x0 is called the center of the Taylor series. Take that, divide it by j factorial, and multiply by x minus x0 to the j. So some examples. These are ones that you should already know and you're going to need to use frequently. So the Taylor series for e to the x. All the derivatives are e to the x, and if we center it at 0, we get the sum as j goes from 0 to infinity of x to the j over j factorial. This is the Taylor series for e to the x centered at 0. This series, in fact, converges for all x and is equal to e to the x for all x. Remember that those are separate questions. So you can write down a Taylor series for a function as long as it has infinitely many derivatives. As long as you can keep differentiating, you can always write down the Taylor series. But there are always two questions then. Does the series that you get even converge? For some x it will maybe, and some it won't, and there can be an interval of convergence. So does it converge is your first question. But then a second separate question is, if it does it converge to the original function? And that's a separate question. For most of the series that we work with, the answers to those questions are, well, the answer to the second question is yes, and sometimes you have to work to figure out the radius of convergence. It's not very common to see an example where the Taylor series converges, but it converges to something different. It is mathematically possible, and you should be aware of that. But for the functions that we work with, we usually don't see that. Okay, but what you're looking at there, Taylor series for e to the x, you need to know that like the back of your hand. You're going to need to use that a lot. Sine. The Taylor series for sine. It converges for all x, and it equals the sine of x. And it has this form. It's negative 1 to the j times x to the 2j plus 1 over 2j plus 1 factorial. The Taylor series for cosine. It also converges for all x and is equal to cosine of x. And it has this form, negative 1 to the j times x to the 2j over 2j factorial. Sometimes you can do manipulations on these things to figure out other Taylor series. For example, let's say I wanted the Taylor series for e to the x, but I wanted it centered at 2 instead of centered at 0. Well, one thing I could do is I could take e to the x, and I could write it as e to the x minus 2 plus 2. Then rewrite that as e squared times e to the x minus 2. And now just plug in x minus 2 into the original Taylor series, the one you see at the top of your screen. So j goes from 0 to infinity of x minus 2 to the j over j factorial. And let's bring that e squared in and make it part of the coefficient in the Taylor series. So it's e squared over j factorial times x minus 2 to the j. So sometimes manipulations like this can help us figure out a Taylor series instead of always deriving it by working out all the derivatives of a function. Now in this beginning section, we're just going to be focusing on the Taylor polynomials. So the Taylor polynomials are what you get when you're writing down a Taylor series, but you stop at a particular n. In other words, they're the partial sums of the Taylor series. So the Taylor polynomials in notation is Pn of x, and here is called the order of the Taylor polynomial, and it has the same form as the Taylor series, but instead of summing from 0 to infinity, we sum from 0 to n. We also with the polynomials, call this the center. X minus x0 to the j. All right, so let's do an example of using this in connection with the differential equation. So in this example, we want to find a fifth order Taylor polynomial approximating the solution to the following initial value problem. Y double prime equals 3y prime plus x squared y, with y of 0 equals 10 and y prime of 0 equals 5. So we know this has a unique solution, and we want to approximate that solution, not find the solution itself, but find an approximate solution in the form of a fifth order Taylor polynomial. Now, of course, one thing that you could do is just try and solve it. And if you could solve it and you had an explicit expression, and then work out its Taylor series, just stop at 5 and there you go. But that would kind of defeat the point. The point of what we're trying to do is have a means for getting some kind of information, some kind of expression for these solutions when we cannot calculate them explicitly. So we're going to find this approximating polynomial without actually solving the differential equation. So the first thing I want to notice is that in my initial value problem that I've got here, x0 is 0. So that means that I want to use that as the center of my Taylor polynomial. So I'm going to center my Taylor polynomial at 0. I'm going to write down the general form of my fifth order Taylor polynomial. So this is the fifth order Taylor polynomial of the solution. The problem is I don't know what those coefficients are. I've got to figure out what that is. And rather than writing it with the sigma notation, I want to write it all out. And I know it's a lot of terms, but it's just going to be easier to see what's going on when I write it all out. So it's y of 0 plus y prime of 0 times x plus y double prime of 0 over 2 factorial times x squared plus y triple prime of 0 over 3 factorial times x cubed, plus the fourth derivative of y at 0 over 4 factorial times x to the fourth, and then lastly the fifth derivative of y evaluated at 0 divided by 5 factorial times x to the fifth. So I'll have my answer if I can find out all those derivatives, if I can get numbers for y of 0, y prime of 0, y double prime of 0, and so on. Okay, well, it's an initial value problem, and I'm given y of 0 and y prime of 0, so those first two are very easy. Come back up to the statement of the problem and see that y of 0 is 10 and y prime of 0 is 5. Okay, now I need y double prime of 0. That's not given to me. However, I am given the differential equation. And the left-hand side is y double prime, and the right-hand side is things that I know, so I can say that y double prime of 0 is 3 times y prime of 0 plus, what is it? X squared times y. Well, x is 0 here, so 0 squared times y of 0. All right, 0 squared, that's gone. So 3 times y prime of 0, that's 5. So 15. Y double prime of 0 is 15. All right, now y triple prime of 0. It looks like I'm out of tricks. So the original y of 0, y prime, y double prime I get from the differential equation. Well, now for y triple prime, what I want to do is I want to take my differential equation here and just differentiate both sides. So if I do that, let's put a question mark here. I don't know yet what y triple prime of 0 is, but in general, y triple prime is going to be, well, I'm just going to differentiate. So 3y double prime plus, and now I need the product rule. I'm taking the derivative of x squared y. So I have 2xy plus x squared y prime. All right, so y triple prime of 0 is 3 times y double prime of 0 plus 2 times 0 times y of 0 plus 0 squared times y prime of 0. All those zeros are great. I don't have to think about anything there. And 3 times y double prime of 0, which is 15, gives me 45. All right, we just keep going like this now until we're done. So the fourth derivative of y. Now what I want to do is take this line here and differentiate both sides. All right, so it's going to be 3 times, let me scroll up a little, 3 times y triple prime plus 2 times y plus 2xy prime plus 2xy prime plus x squared y double prime. Okay, I can simplify that. It's going to be 3y triple prime plus x squared y double prime plus 4xy prime plus 2y. So the fourth derivative at 0 is now 3 times y triple prime of 0. Then I got x squared, so I just get 0. I got an x there, I get 0, plus 2 times y of 0. All right, so that's 3 times 45 plus 2 times y of 0 is 10. So what's that? 135 plus 20, so 155. All right, and the last bit to calculate, the fifth derivative of y, we're going to take this line here and differentiate that. So I have 3 times the fourth derivative of y. Actually, let's look at this line after I simplified it. Okay, plus 2xy double prime plus x squared y triple prime plus 4y prime plus 4xy double prime plus 2y prime. Simplify that. I have 3 times the fourth derivative of y plus 6xy double prime plus x squared y triple prime plus 6y prime. So y to the fifth, evaluated at 0, is 3 times, not y to the fifth derivative of y. 3 times the fourth derivative of y, evaluated at 0, plus, then that's a 0, and that's a 0, plus 6 times y prime of 0. All right, so that's 3 times 155 plus 6 times y prime of 0. What's that? Y all the way back, it's 5. Okay. So what's that? 465 plus 30 is 495. All right, got all my numbers and I can put them in. So my Taylor polynomial, P5 of x, it's just putting those constants in, 10 plus 5x plus 15 over 2 factorial, which is just 2, x squared, plus 45 over 3 factorial, so 3 times 2. I'm going to simplify these. That's why I'm just leaving it as 3 times 2. I'm not writing 6. To make my life easier to simplify it, I just leave it like that. Plus 155 over 4 times 3 times 2, x to the fourth, plus 495 over 5 times 4 times 3 times 2 times x to the fifth. All right, now and simplify. 15 halves, that's simplified already. 45 and 3, that becomes a 15. 155 is odd and not divisible by 3, so that doesn't simplify. The 495 and the 5 become 99, and then the 99 and the 3 become a 33. Okay. So I've got 10 plus 5x plus 15 halves x squared plus 15 halves x cubed plus 155 over 24 x to the 4th plus 33 over 8 x to the 5th. And there it is. That is the 5th order Taylor polynomial, which is approximating the solution to our given initial value problem. Okay, so, and that's it for 8.1, which is just an introduction to the ideas here. And also that's it for this week's material. So I will get your homework and the other stuff posted, and that's it for now. Bye.